Good evening, everyone. I am Darsh Agarwal, and my project is not going to be a generative AI project because I was led to believe that this is the open source AI hackathon. So I'm going to be talking about a lesser known topic in AI, which is very much a backbone of how AI contributes to our society, which is recommendation systems by EasyEats, which is under the track of AI by healthcare. So the context of my problem is that due to current long working hours and high pressure society, we often compromise our health. And this entails consuming ready to eat meals from convenience stores like 7-Eleven, 24/7, Family Mart, and food delivery apps such as Uber Eats, Zomato, Swiggy. And this culture is already extensive and growing in countries like Japan, Korea, India, and the USA. So the market for the ready-to-eat revenue is around $600 billion. So there's a lot of opportunity to capitalize and make an impact in this market. So the crux of the problem is that due to the purpose of these meals, they cannot be a substitute for a balanced diet. For example, they're high in calories, fats, and sugars, and low in important nutrients such as fibers, vitamins, and minerals, right? So therefore, the solution that I have come up with is developing a service that integrates with e-carts of order-to-eat apps, convenience store platforms, and provide recommendations to help consumers make healthier choices. So the roadmap of the project has the following goal: to build a hybrid recommender system. All right. So in recommender systems, the current leading recommender systems are collaborative recommendation and content-based recommendation. However, both of them serve different needs. So collaborative recommendation talks about how likely are you to prefer a product if somebody who is similar to you prefers a product. Whereas content-based recommendation talks about how likely is it that a particular product appeals to you. To hit the perfect mark, to recommend an absolute perfectly meal that not only caters to your health needs, but also to your flavor profiles, you need to take care of both of these things. That's where the lesser known utility recommender systems called utility-based recommender systems come in, specifically implicit utility-based recommender systems. So the big problem with these utility recommender systems is that eliciting the utility, like what I want from a product, from a user standpoint, is very tough. The second thing is they require resources and expertise to implement because of their complex nature, right? So the solutions that we bring with is working with implicit utilities. So as you see in this image, there are two workers who are showing saris to some ladies, and there's this one head worker who's looking at this. So if you notice, after some time, generally what happens is the head worker comes in with a sari that is more likely to be liked by the ladies. That is because this head worker is looking at the behavior of these ladies. Okay, that red sari is something they spent a little more time on. The blue sari was not preferred by them. And therefore, it comes up with a recommendation, okay, this red sari might be the perfect fit for these ladies, right? So implicit utility basically means extracting the utility or the need from the user's behavior itself. And the second problem of complexity can be defeated by innovation and ingenuity that we have. So the big advantages that utility systems present is that they don't have a cold start problem, sparsity problem, and high dimensionality issue. So how the collaborative filtering and the content-based filtering work is they require something called user interaction matrices. And those matrices scale very quickly, very fast in computation because of the nature of matrix operations, right? So that problem is not there. Sparsity, those matrices end up being sparse as in they have a lot of zero values than actual data. That problem is not there. And cold start. Cold start basically means you require a little bit of data to start making useful recommendations. So that problem is defeated. And moreover, utility recommender systems provide a more personalized recommendations and generally have a relevant and customized recommendations which tailor to needs better. So the roadmap is as follows: dataset generation, user requirement generation, user utility extraction, utility function, evaluation fine-tuning, GUI development, and finally, delivering this product as an API SaaS. I'll go through everything in detail so it's clearly understood. So talking about dataset, okay. It was very hard to come up with a dataset that elicits what each and every restaurant delivers at what price and what ratings. Luckily, I came across the scraped source datasets for Uber Eats USA that took around 1 million products all over the US. And I was able to, but the form this dataset was presented to me was in restaurants separately and menu separately. So I converted that into an item-oriented dataset, post which came the big challenge: how to find out exactly how much nutrition value or how much nutrition content is for each product that is being served. So for that, I have utilized generative AI. I have used GPT-4 and I've provided descriptions of each product. And I provided this in a form of function call. So what that does is it makes the LLM assume that it's trying to call a function which produces consistent outputs based on an enum that you provide. For example, let's say I'm giving you a chicken masala recipe. This is the description. Now tell me on low, medium, high, whether the fats are low, medium, high, or the proteins are low, medium, high, and so on and so forth. So for that purpose, for a rough estimate, I'm using LLMs. And based on that, I've generated my data set. So that beats the challenge of generating consistent outputs utilizing function calls. So that is the difference between your standard prompt and what a function call prompt looks like. So something like this was converted into a data set like this. One thing to note is that I've also generated allergens for each product using generative AI. So that we are more mindful of things to recommend, whether they have the required allergens or not. All right. So this data set is doing pretty well on Kaggle. It has 66 views and 13 downloads. Moving ahead, now comes the part of user requirement generation. So user doesn't know what he wants, right? So I have to generate that requirement for him. For that, the primary requirement is a term that you have heard a lot associated with food, calories. So for primary calorie calculation, I'm using age, sex, weight, height, and how active you are throughout the week as 5 criteria from which I extract my utility. So I'm leveraging something called the Harris-Benedict formula, which has been modified in weights but not in core structure since 1914. And the concern with this formula is that it tends to overestimate calories. So suppose you require 1800 calories per day, chances are it will produce 2000 calories. So that's a major concern. 3 minutes more. All right. So the issue that presents with this, so how I've beaten that issue is, I've taken the Mayo Clinic's research. So Mayo Clinic has an independent calculator available. I've taken data, I've scraped data from there, and I've tried 3 techniques, curve fitting, nonlinear programming, and neural networks to match that model. And I've successfully matched that by using algebraic and fit approaches instead of a neural network. And the takeaway from that is fine-tuning an estimate is better than guessing from scratch that a neural network does. So if you have a formula, try to build on that instead of trying to use a neural network to estimate something from scratch. Okay. So other requirements are goal with the meal, whether you want to lose weight, gain weight, maintain weight, and the city that you are in. I'm offering 2 locations right now. And based on that goals, I'm generating, okay, so if you are losing weights, the nutrients are ranked this way. If you are trying to gain weight, the nutrients are ranked this way. And then the final formula to extract utility looks something like this. It is a bidirectional formula, so it punishes meeting the goal or exceeding the goal and coming short of the goal differently. Okay, yeah, so this comes to crux of what I've done here. This is what is the crux of an implicit utility algorithm. So I've taken 2 attributes, that is flavors, in 2 values, so primary flavor of a dish, secondary flavor of a dish. Then I've compared the frequency of the browse item. Suppose, let's say you see 50 dishes on Swiggy. Now you have to see, okay, out of those 50 dishes, 20 of them were savory, 10 of them were sweet. So based on that, I'm calculating, let's say I'm getting a new flavor called herbal. So based on that, how herbal stands in comparison to the least frequent flavor and the most frequent flavor, that is where you get your attribute value. And the time spent on each product is also calculated in something called a holistic utility. I am combining these 2 things in a non-linear programming function here, and the goal is to minimize this difference, because if I'm spending a lot of time in something, chances are I like its flavors, right? So I'm using 2 techniques, SSSQP and genetic algorithms. Now the thing is, genetic algorithms are the standard approach, but what I've introduced is a SSSQP. I'll quickly go towards why, because I'm in lack of time, because as you can see, genetic algorithm produced an output in 25 seconds, whereas SLSQP produced it in 0.9 seconds. And when you compare genetic algorithms who are already faster compared to stuff like Smarter, you are working at speeds of 5.89 per second in comparison to 320 seconds, right? So that's the beauty of SLSQP. Now the issue is genetic algorithms are supposed to overcome the barrier of discontinuous functions, right? But luckily, yeah, but luckily in our scenario, what we have in a recommender system is a spherical function. So as you can see, a minus ix plus b minus jy, those are essentially attributes. The more attributes you increase, it will become a sphere, then a 4D sphere, then a 5D sphere. So the crux of the point that I'm trying to drive here is it will always remain a continuous function. So therefore, I can use sequential least square programming to reach the minima always, which will land around this square and intersection between this circle. So playing around with these parameters, I will always land to the closest value, and my goal is to minimize that C. That is your final utility. So this is my architecture. It uses basically multi-attribute utility concepts, and it uses SLSQP. So the code walkthrough, I think I have done enough, so I'll just quickly go through that. So a demonstration is in order. So as you can see, I've provided a 162 centimeter height female with a weight of 65 and age of 45, who's lightly active and wants to lose weight and lives in Austin. She should go for these items. And you can put any weight, any height, anything, and you will actually have real-time data from Austin and Dallas. All right. So concluding quickly, so I had a lot of great learnings and a big word of appreciation to the community for support, especially Bharat, who was there with me for every step of the way. So one thing I would like to add quickly is the open source landscape for recommender systems. It is very bleak, and it is only oriented towards collaborative filtering and content filtering. And due to that, a lot of options are limited due to the high compute required. By eliminating the need of compute and producing a lightweight model, I'm contributing to the promotion of utility-based recommender systems in open source environment by coming the shortcomings of the open source, like of the utility softwares, by utilizing the open source medium itself. So by using open source data, by using open source functions, I'm able to beat that complexity problem that utility functions present. Lastly, in the landscape of meal solutions, this project can be a contribution in promoting health-oriented food choices via the medium of open source software. So people will try this, more people will, okay, if somebody is working towards this must be important. I should pay attention to my health. Yeah, just last slide if I may. Yeah. So my conclusion and takeaways are this, that I've built a public study on model mimicry. So I've successfully able to interpolate the Mayo studies on how to calculate calories. I've built an open source, extremely lightweight and fast recommendation algorithm that is versatile and can be used in recommendations problems, especially in user-oriented recommendation problems. And I've worked towards an impactful solution towards a relatable emerging problem. Thank you so much. I'm open to questions now.
All right. Thanks. Just to clarify, you just finished your high school now, right?
Oh, no, I'm a third year undergraduate. Yes. Okay.
All right, cool. Questions? Shubha is going to have a lot of questions. I don't know if you have context here. Shubha leads quite a bit of ML stuff at Swiggy.
Yeah, actually, one thing on the recommendation systems, maybe we need a bigger discussion on that, because real-time recommendation systems really don't use these large-scale matrix operations. I mean, there are other ways to do it, and I mean, kudos to your effort, but some of the problem statements that you mentioned earlier, right, that the cold start problem is solved, the data sparsity is handled, that how exactly is done is not coming through.
Okay, sure. So the issue with sparsity is that basically the methods that you have, collaborative filtering or content-based filtering, they
here sparsity in terms of the user whatever.
No, sparsity
item
instead of sparsity in the sense of the computation itself. So in my RDD, I have a lot of zeros instead of ones because of the lack of user interaction. That's the cold start problem. I do not have enough data on my users themselves, so I cannot link them together, or I cannot link a product to them together.
But even in other utility-based functions, let's say if there is a new user coming to the platform, we actually don't have information about such users.
Yeah, so but the idea is that what you're doing is you're just taking very minimal data from them instead of relying, and the best part is that all you need is user interaction with the app for the flavor profiling, right? So even if you do not want to provide physical credentials, just based on the behavior, I can guess at least the user profiles that you're working with, right? So flavor profiles. So instead of, let's say, if I'm trying to recommend you a protein milkshake instead of an ice cream, right? And I saw you scroll through a lot of butterscotch ice creams. So I'll directly go to a butterscotch milkshake and recommend that to you instead. So even that is a step where you require no input from users, just their latent passive attributes of how much they're scrolling on a particular item and what is the frequency of certain attributes showing in a particular item, you can get a lot of information about the user
Yeah,
and use it.
typically we don't have to, actually the customer doesn't have to click anything.
Yeah.
We are, even if what they're spending more time on, those kind of inputs are obviously taken into the recommendation. One more point. There was one where you are extracting the health, what is that, proteins and all of that, right, through the LLM. But that really depends on, say, two different restaurants. Literally, it's like maybe some paneer, palak paneer or something. They will have completely different calories. So how reliable is this information in recommendation?
So exactly. So the current challenge with this whole problem is that data. Currently, the project can massively benefit from verified nutritional data from restaurants, right? So right now, to prove drive home the concept that recommendations can be very, very easy given the data is there. So I've just generated some pseudo data that serves as a placeholder. Okay, like so if I'm working with a chicken curry, the LLM is able to generate a so-so estimate. Okay, if I choose a chicken curry based on this description, I'll be having this nutrients. One thing to note here is that each restaurant has described their products differently, right? So that also affects the nutritional content that is being provided for the same chicken curry. However, as obviously LLMs are no nutritionists, so you won't be able to get a proper response. That is why the open source contribution part of this project can be providing more verified data. And today I interacted with a gentleman who actually works in this area, like crowdfunding data on recipes, crowdfunding data on different restaurants and their food items and their nutritional contents. So that is something that is a future scope of it, actually working with solid data. So for example, if I'm able to work with Swiggy, right? A lot of times, a lot of restaurants are listing their data on Swiggy now. So this would drive home that point really well, that I'm working with an actual data and that data will show even better results than this. Because for example, here, if you see, I am recommending prosciutto mozzarella sticks. Nobody in the right mind would have that in their meals, right? But just because of the nature of data, I'm getting that as a recommendation, right? But if I have actual meals with actual data, actual content of nutrition, the model will be able to perform much better. So currently, this whole application is being held back by the absence of data.
Yeah, I think one last question. I think again the common theme. See, it's part of, now you are building a recommendation system.
Yeah.
There are some metrics to measure the quality of the recommendation. Like, how do you think you will be able to measure that?
Oh yeah. So what I've done is I've leveraged a sort of a Euclid's axiom that if A is greater than B and B is greater than C, A should be greater than C. Obviously, that has a lot of caveats to it. However, what I'm trying to drive home here is that I've compared to a already studied model, that is implicit utility with genetic algorithms, and I'm comparing it with my model, that is implicit utility with SLSQP, okay? So I've already seen IUGA beating a lot of models, and on same parameters, I'm running my model, which is beating.
So what are those metrics you're using?
Yeah. So just let me switch to the presentation. So one thing is that in time expense, it's beating like a lot of models by huge margin.
No. Quality of recommendation.
Yeah, and in quality of recommendation, if you see the results from a IUG algorithm, the results that are produced by the SLSQP algorithm are pretty close. So then we can rely that, okay, this is a tested method. I'm producing results similar to that method. That means like my model is bound to perform decently. That is only the conjecture that I have. I obviously like I would require, so again, looking ahead here, so beta testing on platforms to actually validate the model is something that I look forward to. So I need actual impact that I have generated this recommendation. So whether a person is putting it in a cart or not, that is something that has to be validated, and that is the only way to do it.
Okay, very interesting work. One specific question I had is the metric that you designed, right? Was around the dimension of flavor.
Yeah.
How do you incorporate other dimensions like time of ordering, the emotion, the mood of the person?
Yeah.
Would that be able to incorporate that?
So yeah,
that's one, and then the corollary to that same thing. Like, how do you validate it? Like, for example, you suggested a kind of items to one customer. How would you validate that that's a good one, and would it generate a different type of recipe next time? Because every day, if it is, let's say, suggesting mozzarella sticks,
fair enough.
Then it may not be a good suggestion.
So coming here, I'm taking account. Okay, there's a better example for that. Here. So if you see here closely, the reason the mozzarella sticks are so high up is because of their price. So price is also part of an explicit utility that I'm using as a function. So similarly, I can add delivery times as well here. So I can give, the lesser the delivery time, the better the utility. So I'm already including price and ratings as my utility. So how are they weighted? Yes. So do you want to see the function? Yeah, it's incorporated. And the idea is I am subtracting ratings out of 5 because I'm trying to make a minimized function. So the higher that number, so if I get 4.9, so I'll get 0.1. That's better than 4.6, that is 0.4. So that is how I'm working with. Same with price. I'm taking a price normalization formula under the range of $0 to $30. And then I'm saying, okay, $1 price is really good because I'm trying to minimize it again. Coming to your second point about improving recommendations. So the final metric of this paper, how they judged everything that I'm referring to here, is that they judged their final output based on if a person put that item in their cart or not. Similarly, if I'm given an opportunity to create a model or test like that, I will be able to generate similar results. And based on that, there will be a third metric introduced, that is click rate. So if a product is clicked through more, that is supposed to be highlighted better. So how your recommendations will be divided is, as you might have seen, top picks versus new recommendations. So that way you can divide, okay, these are your classic favorites, so they'll come in top picks, and your new recommendations will come in fresh recommendations based on what you click. So based on those clicks, your flavor profiles will be highlighted, okay, so this person is ordering 5 savory meals, so a 6th recommendation should be also something like savory, right? Or there could be contrasting functions, right? So I can maximize the function instead, okay, this person is leveraging savory food, I should recommend something sweet instead.
All right, thank you. Yeah, all the very best.